Good day, everyone. So our topic today is about chemical bonding. Okay, so chemical bonding, almost everything we see or touch in our daily lives is the result of chemical bond. The air we breathe, the food we eat, the clothes we wear, and so on. And they are all made up of one or more chemical bonds. But why do you think you have to study chemical bonding? Okay, so what is chemical bond? Chemical bond is a strong attractive force that holds particles or atoms together to form ions or molecules in a chemical process. So again, why do you have to study chemical bonding? You know, Forensic science uses technological and chemistry to gather and analyze evidence about crimes. Forensic scientists have a standard repertoire of chemical agents for their work. So these chemical agents can reveal evidence that may be hidden to the naked eye and produce clues to what happened at the crime scene. And these chemical agents are actually products of chemical bonding. Well, if you're a crime investigator, you should know that fluorescein causes a chemical reaction between oxygen and the hemoglobin present in blood. So this chemical is useful for fine blood stains and smears, which may appear in different crime scenes. Or let's say another chemical used for blood evidence is luminol. So like other blood test chemicals, it reacts with iron in the blood. All right. So luminol can reveal blood evidence even if someone has tried to clean the blood off. Well, you will know more about this in forensic chemistry. All right. So all these chemical reagents are products of chemical bonding. Okay, so this is just a review. Oftentimes, people think that atom and molecules are the same. They are not, right? Since atom is a basic unit of element, while molecule is a group of atoms held together, basically nonmetals. All right. Now, the chemical bonding are broadly classified as covalent bonding and ionic bonding. In covalent bonding, there is a sharing of electrons between two or more nonmetals. Unlike covalent bonding, ionic bonding occurs when there is a transfer of electrons from metal to nonmetals. All right? Now, there are two types of covalent bonds, polar covalent bond and nonpolar covalent bond. So there's an unequal sharing of electrons that results to polar covalent bond. And the shared electrons becomes partially, partially charged. So it's either positively or negatively. So this is still between two nonmetals. For example, hydrogen and fluorine, or nitrogen and oxygen, or carbon and oxygen. On the other hand, nonpolar covalent bond is formed through equal sharing of electrons of two nonmetals. So usually this is between two same kind of atoms, like oxygen and oxygen, nitrogen and nitrogen, or hydrogen and hydrogen. So we will talk more about this covalent bonding later on, since this is very important in organic chemistry. Okay, so here are some examples of nonpolar covalent bond. So we have same kind of atom, which is chlorine and fluorine, and there are no charges formed, okay? And then we have the polar covalent bond. So we have two nonmetals. So we have hydrogen and chlorine, and both atoms become partially charged. They are partially charged, okay? And then we have ionic bond, which is resulted from bonding of a metal and non-metal. So we have sodium as metal and then fluorine as non-metal. Now, listen carefully. Covalent bonding produces molecules, while ionic bonding produces ions. Okay, take note of that. That's why you have chlorine molecules, HCl molecules, and then you have NaCl ions. All right. All right. So look at your periodic table and find the electronegativity value of each element. Okay, we can determine the type of bond through the electronegativity difference between two atoms. So what is this electronegativity? Electronegativity is the measure of an atom's ability to attract electrons. All right, so for polar covalent bonds, so this is between two different kinds of atoms, right? So this is the symbol for higher electronegative atom. Okay, so this is a symbol for higher electronegative ions or atoms, and this is the symbol for lower electronegative atom. Now, for ionic bonds, this between metal and non-metal. Okay, so try to recall our lesson in an atomic structure. So non-metals gain electrons and form an ions. So therefore, they have higher electronegativity, while metals loses electrons and form cations. So therefore, they have higher or rather lower electronegativity. Okay. All right, here's the electronegativities of the elements. So we have for hydrogen, it's 2.20. And then lithium, we have 0.98. Beryllium, 1.57. Boron, it's 2.04. Carbon, 2.55, and then so on. Now, these noble gases have no electronegativity. Okay, so we have helium, neon, argon, krypton, xenon, and radon. They don't have electronegativity since they are stable elements. Okay, so of course, there's a trend. So from left to right, the electronegativity values of the element increases, and from bottom to top, it increases. All right. So we can determine the type of bond through electronegativity difference. So we have this range. So electronegativity difference from 0 to 0.3, it's non-polar covalent bond. Then 0.3 to 1.7, you have polar covalent bond. And if the electronegativity difference is greater than 1.7 up to 3.3, then that is ionic bond. Okay, I hope you understand. Now, the measure of bond polarity is the dipole moment, okay, which has the symbol of mu. Okay, mu. And as I have said earlier, these are the symbols of partially charged atoms. Okay, these are the symbols of partially charged atoms. And this arrow is the direction of your dipole moment. All right. So the direction of the dipole moment goes from lower electronegativity to higher electronegativity. Okay. So let's have some examples. So we have chlorine molecules, so Cl2. So Cl2, the electronegativities, so we have 3.16 minus 3.16, so it's 0.0, the electronegativity difference. So therefore it is nonpolar. All right. Now, it has no dipole moment. Okay, it has no dipole moment. Now for HCl, okay, so the electronegativity of chlorine is 3.16, and then the electronegativity of hydrogen is 2.2. So you just have to get the electronegativity difference. So you just have to subtract 2.2 from 3.16. So you get 0.96. And that falls on, okay, so that is polar covalent bond. All right. And the direction of the dipole moment is from hydrogen to chlorine. All right. So this is the direction of your dipole moment. Hydrogen to chlorine, since hydrogen has lower electronegativity compared with chlorine. All right. And then sodium chloride, NaCl. So electronegativity of sodium is 0.93, and then chlorine is 3.16. So the difference is 2.23, and that falls on ionic bond. Okay, so the direction of your dipole moment is, all right, so from lower to higher. That should be from left to right. All right. So please just correct that. Okay, so let's have a challenge problem. So this is a giveaway. Give the electronegativity difference and predict the direction of the dipole moment of carbon and sulfur, nitrogen and boron, nitrogen and sulfur. So first 5 students who will message me the correct answers will get plus 5 points on the third quiz. All right. Okay, so for you to understand better, let's look at this example. So the chemical bonding is like the game tug of war. Okay, so tug of war. So this is a tug of war between atoms. So the electronegativity is like a tug of war game between atoms or 2 atoms. If you have one person, all right, if you have one person on the side of the rope, wait, okay, so if you have one person on the side of the rope that is stronger than the other person, then that stronger person will tug harder, pulling the other person in their direction. All right. On the other hand, if you have 2 people of equal strength, then the rope would not shift in any one direction and stay in the same place, right? All right. So like tug of war, you have a stronger atom with a higher electronegativity. Then it will be able to tug electrons in their direction. Okay. So let's have another example. Okay, so you have to use electronegativity values to classify bonding between sulfur and hydrogen, cesium and fluorine, chlorine and phosphorus. Okay, so for sulfur and hydrogen, so you have the electronegativity difference of 0.4, and then the bond type is polar covalent. So the more negative atom is sulfur. All right. And then okay, so this is the direction of your dipole moment. Okay, so from hydrogen to sulfur. And then for cesium and fluorine, so you have the electronegativity difference of 3.19. So that falls under ionic bond. Okay, the more negative atom is the fluorine, and the direction of your dipole moment is, all right, from cesium to fluorine. Okay, and then for chlorine and phosphorus, the electronegative difference is 0.19. So it is a polar covalent bond. So the more negative atom is the fluorine. And the direction of your dipole moment is from phosphorus going to fluorine. All right? So since chlorine is more electronegative. And then oxygen and oxygen. Okay, so this is a nonpolar covalent bond since it has an electronegative difference of 0.0, and of course it has no dipole moment. Okay, since the electronegative difference is 0. Okay, now how does bonding work? So this is the critical part. How does bonding work? So let's say we have two atoms. Let's say lithium is a metal and then chlorine is a non-metal. And then, so yeah, they will form ionic bond. So how does it work? So by using their electron configuration, okay, so let's use fluorine. Okay, and lithium. So fluorine has an electron configuration of, okay, and then, so that is 1s2, 2s2, and then 2p5, all right? And then lithium has 1s2 and then 2s1. So the valence electron of lithium is 1, and then the valence electron of fluorine is 7. So fluorine is at second energy level, okay? So the highest energy level has 7 electrons. So that's the valence electron of fluorine. All right, so remember octet rule, okay? All atoms must have 8 electrons in their outermost energy level to become stable. But of course, there are exemptions, and that's hydrogen and lithium. Anyhow, lithium is in excess of 1 electron to become stable, right? So it has an excess of 1 electron to become stable. While fluorine is in need, okay, is in need of 1 electron to become stable. Okay, so 2 electrons at the outermost energy level will make lithium stable, while fluorine needs to have 8, all right, 8 electrons in the highest energy level to become stable. Since it only has 1, 2, 3, 4, 5, 6, 7, so it needs 1 electron. While lithium, it just needs to have 2 electrons to become stable. So what we have to do is to transfer 1 electron of lithium to fluorine. So both will become stable. Okay, and this is what you call the ionic bonding. Okay, so there is a transfer of electrons. Okay, so this is an ionic bond. So ionic bond is then formed between lithium and fluorine. Now let's have an example for non-polar covalent bond. So let's have 2 fluorines. Okay, so 2 fluorines with electron configuration of 1s2, 2s2, 2p5. Okay, so the number of electrons in the highest energy level, or the valence electron, is 7. So both needs 1 electron in the outermost energy level to become complete or stable. Since they are both non-metals, they are both greedy, right? So they are both greedy and none of them want to give up their electrons. So what will happen is that they will share, okay? They will share each other's electrons. So fluorine 1 will have 1, 2, 3, 4, 5, 6, 7. Sorry, 1, 2, 3, 4, 5, 6, 7, 8. Okay, and fluorine 2 will have 1, 2, 3, 4, 5, 6, 7, 8. All right, and they formed non-polar covalent bond. Okay. Okay, and finally, for polar covalent bonding, let's have oxygen. Okay, with the electron configuration of 1s2, 2s2. Okay, so we have 2p4. So the valence electron is, okay, so the valence electron is 6, okay, for oxygen, and then 1 for hydrogen. So the valence electron is 1, all right. So therefore, oxygen needs 2 electrons, okay? It needs 2 electrons. So 1, 2, 3, 4, 5, 6. It only has 6 valence electrons, so therefore it needs 2 electrons to become complete or to become stable. So what you have to do is you have to add another hydrogen. Okay? So oxygen shared 2 electrons, and each of these hydrogen shared 1 electron. So they would become complete. So let's count. So we have for oxygen, 1, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay? And same goes with hydrogen. So you have 1 and then 2, and then 1 and then 2. So they form the polar covalent bond. Okay? You can have a knowledge of this chemical bonding with your human relationship, you know. What do you think? Okay? So anyhow, so you know that covalent bond occurs when there's interaction between 2 or more nonmetals, like water, carbon dioxide, or glucose, which is also known as sugar. Okay, so in this type of chemical bonding, there is a sharing of electrons between 2 or more atoms. All right. So now, here's some of the vocabularies that must retain in your head. The covalent bond, I told you about it a while ago, is the sharing of 2 or more atoms or nonmetals. Then molecule is a group of atoms held together. And molecular compound is a chemical compound whose simplest units are molecules. Okay, so a chemical formula is a notation used by scientists to show the number and type of atoms present in a molecule using the atomic symbols and numerical subscripts. All right, so here are some of the examples. We have the sodium chloride, which has the chemical formula of NaCl. Okay, and then we have the, okay, CH2O, and then we have the C6H12O2, both chemical formula of glucose. Okay, these are both chemical formula of glucose, and this is the simplified form. You will know more about this on how to deal with this kind of formula later on. So you can have ionic compound or covalent compound from this. Okay, so while molecular formula is one type of chemical formula which consists of the chemical symbols for the constituents elements followed by a numeric symbol, okay, or numeric subscripts. So it describes the number of atoms of each element present in the molecule. So basically, Molecular formula is a term used for organic compounds. Okay, this is the term used for organic compounds. So some example of this is CH4. So CH4 is also known as methane. And then we have the C6H12O6. So as I have told you, it's a molecular formula for glucose and all other compounds. All right. Now let's look at the difference between intramolecular force and intermolecular force. So intramolecular forces occur between atoms. All right. And intermolecular forces occur between molecules. So intermolecular forces is applicable to covalent compounds, while intermolecular forces is for ionic compounds. Okay, and it is much more stronger than intermolecular forces. Okay. Another vocabulary that you must be familiarized with are the bond length and the bond energy. So bond length is the distance between two bonded atoms at their minimum potential energy, while bond energy is the energy required to break a chemical bond. So when forming a bond, atoms releases energy. Okay, so the same amount of energy must be added to break the bonded atoms. Okay, so here are some of the examples. Okay, so you just have to think of a pencil. So a short pencil is much harder to break than a long pencil, right? So if there are two or three pencils together, they would be even harder to break. All right. So this is how bond length and energy works. So we will talk more about this bond length and bond energy in our succeeding lessons. Now let's go back to octet rule. You know that the octet rule refers to the tendency of an atom to prefer to have 8 electrons in the valence shell, right? So when atoms have fewer than 8 electrons, they tend to react and form more stable compounds. Okay? All right. So this octet can be made up by own electrons and some electrons which are shared. Well, well, actually, an atom continues to form bonds until an octet of electrons is made. Okay? Okay, now, so let's apply octet rule in fluorine atom, which has electronic configuration of 1s2, 2s2, 2p5. So the number of valence electron, all right, so the number of valence electrons in the outermost energy level or highest energy level or highest period number, which is 2, is 7 electrons. Okay, so we discussed this earlier. So it has 7 valence electrons. So these valence electrons indicate that fluorine needs 1 electron to become stable. Okay, so this is just the same as our previous examples. So we can have another fluorine and they will both share 1 electrons to become stable or to become complete. Okay, so this is the octet rule. So here, shared pair or bonded electrons of fluorine and okay, so this is a bonded pair of electrons of fluorine. And these are the lone pairs. Okay, so these are the lone pairs or unbonded electrons of fluorine. Okay, now, how did they become complete? So let's count. So it would be 1, 2, 3, 4, 5, 6, 7, 8. All right. So to show their chemical bonding, we can write this as F2. Okay, so remember that one, okay, so this one bond is equivalent to 2 electrons. All right, so this is what we call the single bond. All right, so when we count this 1, 2, 3, 4, 5, 6, 7, and then 8. Same goes with the other fluorine. You will have 1, 2, 3, 4, 5, 6, 7, and then 8. Okay, so let's have another example. For oxygen, let's say we have oxygen. So oxygen, we have the formula or electron configuration 1s2, 2s2, 2p4. So the valence shell or valence electron of oxygen is 6. Okay, so 1, 2, 3, 4, 5, 6. So therefore, oxygen needs 2 electrons to become complete, right? So what you have to do is that, okay, so each oxygen has to share 2 electrons with each other. All right. So therefore, it would become 1, 2, 3, 4, 5, 6, 7, 8. And if we will use the bond, it would become 1, 2, 3, 4. A single bond is equivalent to 2 electrons. So therefore, 5, 6, 7, and then 8. Same goes with other oxygen. So you will have 1, 2, 3, 4, 5, 6, 7, and then 8. So this is what we call the double bond. Okay, so let's have another example. Okay, so nitrogen. Nitrogen has an electron configuration of 1s2, 2s2, 2p3. Okay, so 1s2, 2s2, and then 2p3. Now, okay, the valence electron of nitrogen is 5. So 1, 2, 3, 4, 5, which means that the nitrogen needs 3 electrons to become complete. So that's why if you have 2 nitrogens, therefore, they will share 3 electrons with each other. All right? So it would have 8 electrons in their outermost energy level. So this is what we call the lone pair. And then these are the 3 shared pairs. Okay? So therefore, if you will count, if you will change these 2 electrons into bonds, you will have 3 bonds. Okay? So we have 1, 2, 3, 4, 5, 6, 7, 8. So therefore, nitrogen is now stable or complete. And this is what you call the triple bond. Okay? That is the triple bond. Now for diatomic elements, okay, in the periodic table, there are 7 diatomic elements. So these are hydrogen, nitrogen, oxygen, and the halogens, fluorine, chlorine, bromine, and iodine. So these are the diatomic elements which they cannot stand alone in a chemical process. They always go in pair. All right? They always go in pair. Okay, now there are exceptions in the octet rule. The atoms or elements that can hold 8 electrons. Okay, just like hydrogen. Okay, since hydrogen can only hold a maximum of 2 electrons. And then boron, it can only hold 3 electrons. So basically, those elements from period 3 and below, aside from hydrogen and boron, can form bonds with expanded octets. However, we will not talk about it since those are ionic compounds. All right? They are ionic compounds. So we are more concerned with covalent compounds since this is organic chemistry. So we are just dealing with molecules or molecular compounds. Okay, so just a recap. So covalent bond occurs between two nonmetals. Okay, so just remember that. So let's go to Lewis structure. Okay, so what is Lewis structure? So it is the shorthand representation of the valence electrons in a molecule. So let's have, okay, CH3I, okay, or methane iodide as our example. So it has 3 lone pairs or 6 unpaired electrons, and then it has 4 shared pairs or 4 paired electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. So these are the lone pairs. Okay, 3 lone pairs. So 1, 2, 3. Or it is also 6 unpaired electrons. 1, 2, 3, 4, 5, and then 6. And then we have the 4 paired electrons. Okay, for this Lewis structure. So 1, 2, 3, 4. So this is the Lewis structure of methane iodide. So how many total electrons are represented in this structure? How many do you think? So there are 14 electrons. All right, there are 14 electrons. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right. Okay, so here's the Lewis structures guidelines. So the first one, you have to count the number of valence electrons needed. Okay, so this is very important. You have to count the number of valence electrons needed. Okay, so for example, in our CH3I, so we have the valence electron for carbon is 4. Okay, so this is the valence electron of carbon, which is 4. The valence electron of hydrogen is 1. Okay, 1. Now, hydrogen, there are 3 hydrogen atoms. So you have to multiply that 1 by 3. And then the valence electron of iodine is 7. So you just have to get the sum of all this, and that is 14 electrons. The next is you have to set up the skeletal structure. So the rule here is that the least electronegative element is the central atom, or the one that has the less valence electron is your central atom. Siya yung nasa gitna. Okay? So if carbon is present, you have to use it as the central atom. However, hydrogen and halogens are never central atoms since they can only form one bond. Okay? So therefore, your carbon is at the center. Okay? And then you will make a skeletal structure. All right? Okay, so let's have an example. Let's say we have this C2H4. Okay, so the first step is you have to count the number of electrons. Okay, so carbon has a valence selection of 4, and then you have 2 carbon atoms, so that would be 2 times 4. And then hydrogen has 1 valence selection, and you have 4 hydrogen atoms, so 4 times 1. So get the sum, you will have 12 electrons. Now, next is you have to set up the skeletal structure. So you have 2 carbon atoms. So you have 1 and then 2. Then you have 4 hydrogen atoms. So you have 1, 2, 3, and then 4. So give all atoms, the next step is you have to give all atoms an octet by adding lone pairs. Okay? Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you have to check, make sure that all atoms have an octet. And then count electrons to match the number of electrons required for the compound. So you have 14 electrons. So you have to remove those 2 electrons and then replace it with double bond. All right. So now you can count it again. 1, 2, 3, 4, 5, 6, 7, 8. Same goes with the other carbon. You have 1, 2, 3, 4, 5, 6, 7, 8. Now hydrogen only needs 2 electrons to be complete. So you have 1, 2, 1, 2, and so on. Okay. So you have the double bonds. Now let's try the triple bonds. Okay, so you have valence electron of carbon is 4, and then multiply it by 2, since you have 2 carbon atoms. And then hydrogen valence electron is 1, and then you have 2 hydrogen atoms, so multiply by 2. So your number of electrons needed is 10 electrons. And then next is you have to set up the skeletal structure. All right. So you have 2 carbon, okay, and then you have 2 hydrogen. Okay. Now give all atoms an octet by adding lone pairs. So carbon, you have 1, 2, 3, 4. There are only 4, so you have to add. All right, 4. Okay. So now you have to check to make sure that all atoms have an octet, and then count electrons to match the number of electrons required for the compound. Okay. Now if you have uh, 4 too many electrons. Okay. So therefore, you have to remove those uh, unpaired electrons. So therefore, you will have replace it with bonds. So you will have triple bond. So you can count this as 1, 2, 3, 4, 5, 6, 7, and then 8. So therefore, in this Lewis structure, you have 10 electrons. And we have the triple bond. Okay? Now, to check if your answer is correct, you have to use the formal charge. Okay, so the formal charge of this is equal to 4, okay, minus 0, minus 8 over 2. Okay, so what is this H? Okay, so hydrogen and halogens form one bonds. Okay, this is still part of the guidelines. So we have, okay, halogens are those elements in group 17. Okay, so these are the fluorine, chlorine, bromine, iodine. So it is always on the ends, never the central atom, hydrogen and chlorine. Now, oxygen always forms two bonds. Okay, it always forms two bonds. You just have to remember that. And then while nitrogen always forms three bonds. Okay, it always has three bonds. And then carbon forms four bonds. So you don't have to think about it or how many bonds do they have. Automatic carbon has four bonds. Okay, so possibilities to remember carbon, nitrogen, and oxygen can form double bonds. Now, carbon and nitrogen can form triple bonds. Now, let's try this. We have to draw the Lewis structure for CCl4. Okay, so CCl4, you just have to count the valence electrons needed. So I start with a skeletal structure. So element with the lowest electronegativity goes as central atom, and that is the carbon. So carbon is always the central atom. Okay, so if two carbons, they are attached. Okay, so hydrogen and halogens are never central atoms. Okay, so we have to add lone pairs. Okay, so these are the lone pairs. And then we have to check for octets on every atom. Okay, so do they contain 8 electrons? So we have 1, 2, 3, 4, 5, 6, 7, 8. And then for carbon, you have 1, 2, 3, 4, 5, 6, 7, and then 8. All right, so they are complete. Now for C2HCl, so you once again have to get the total valence electron, which is 16 electrons. So, and then Lewis structure. Okay, so hydrogen, carbon, carbon, and then chlorine. Okay, so make sure it matches the electrons needed. Okay, so you have triple bond between the two carbon. Okay, now you have to draw the Lewis structure for CCl4, right? Okay, so this is our structure. Now, how can we find the formal charge? So let's start with carbon. Okay, so carbon, you have 4 minus 0 minus 8 over 2. So if the formal charge is equivalent to 0, therefore, this is a plausible Lewis structure. Okay? And then for chlorine, by the way, 4 is the number of bonds. Okay? This is the number of bonds or the paired electrons. And then 0, this is the number of unpaired electrons. I have a formula here. Okay, there you go. So formal charge is equal to the number of valence electron. Okay, the number of valence of electron of carbon is 4. And then the number of unbonded electrons. So carbon has no unbonded electrons minus the bonded electrons. So the bonded electron, number of bonded electrons is 8. So 1, 2, 3, 4, 5, 6, 7, 8 divided by 2, and that would be your formal charge. So if the formal charge is 0, therefore your Lewis structure is plausible. Now for chlorine, So the valence electron of chlorine is 7 minus the number of unbonded electrons. You have 1, 2, 3, 4, 5, 6. So you have 6 unbonded electrons. And then for the bonded electrons, you have 1, 2 divided by 2 is equal to 0. Okay? So this can also be equivalent to number of bonds. All right? So since the answer is 0 for chlorine, so therefore this Lewis structure is plausible. Okay, so let's have another one. C2HCl. Okay, so you have 16 electrons. Okay, 16 valence electrons. Okay, so 16 valence electrons. So we have to find the formal charge to know if this structure is plausible. Okay, so the formal charge is equal to, so for carbon, you have 4. Okay, the number of valence electron, you have 4 minus the unbonded electrons, which is 0. Okay, minus the number of banded electrons, or the number of bonds, which is 8 over 2 is equal to 4. So it is 0. So this is plausible. Now we can find for hydrogen. So it would be valence electron is 1, unbonded electron is 0, and then the number of bonds is 1, or number of bonded electron divided by 2. Okay, so you have 1. Okay. Now, there are some exceptions to this. So take note of this. The carbon monoxide. Okay, so carbon monoxide. Okay, so carbon has 4 valence electrons, and then oxygen has 6. All right, so in this case, our guidelines doesn't work actually. However, you can still get the uh, triple bond for carbon monoxide. Now let's have a challenge problem. Okay, so you have to draw the Lewis structure and find the formal charge for CH2O and CH3NHCH3. So first, students who message me the correct answers will be exempted, and the succeeding 3 students will get plus 5 points on the third quiz. All right? Okay, so let me just introduce to you the resonance. This is when a single Lewis structure does not clearly represent a covalently bonded molecule or ion. So resonance is shown with a double-headed arrow placed between the molecules' resonance. So there might be times that you would get the same answer, the same number of electrons, but you have different structure. And this is like a mirror, okay? So your answer is still correct, okay? It's just a slightly different structure, but this is actually the resonance, okay? So you will know more about this when we reach the next lesson, all right? So that's all for today. Thank you. Stay safe.